Today I'm going to talk about a paper on determining a risk-based water quality threshold for coliphage in surface waters of different temperatures. This work is summarized in a peer-reviewed paper shown at the bottom of the slide. Coliphage are diverse viruses that infect E. coli, and they're excreted in stool and found in very high concentrations in sewage. And they've been used to assess surface water quality for many years around the world because they're thought to better mimic viral fate and transport. But currently there are no guidelines to assess if coliphage levels are safe. So the goal of this study is to use a modeling approach to figure out what is a risk-based threshold for coliphage in surface waters. The general overview of the method is here. So we use quantitative microbial risk assessment to model a simple hazard scenario where sewage is the contamination source for coliphage. In this scenario, coliphages serve as an indice for the amount of sewage and pathogens present in the bathing water. And we consider the aging and decay of organisms using a first order decay rate constants from systematic reviews of the literature. And the model considers transport of the microbes by considering dilution, and the model was implemented in R. The hazard identification and exposure scenario is outlined here. Raw sewage with coliphage and pathogens leaks into surface waters where a swimmer is exposed to the coliphage and pathogens sometime tau later. The surface water contains dilute sewage and coliphage and pathogens, and we can measure the concentration of coliphage to get a concentration C measure. And then we also have a concentration in the surface water of each pathogen, Ci subsurface. Here's some mathematics behind the model. The concentration of pathogen I in surface water is calculated using information about the ratio of the indicator and pathogen in sewage and the measured concentration of the indicator in the water. We also have to consider the potential decay of the indicator and the pathogen over time. We calculate the probability of illness for each individual pathogen using dose response curves that consider dose of the pathogen, and then we sum all of the different, we consider contributions to total illness risk from all the pathogens. For each time we run the model, we specify what C measure is, that is the concentration of coliphage and the age of contamination tau, and then used in each model, we use distributions for the volume, different K values for sort of decay rate constants and concentrations of pathogens in sewage, as well as dose response models. I don't have time to provide all of these model inputs in this short presentation, but they're outlined in the model, and they come from systematic reviews in the literature. We use a Monte Carlo simulation to run each combination of tau and C measured to see what the risk-based thresholds will be for different ages of contamination. So here's the first slide of results. What this shows is for each model run, the distribution of probability of illnesses. So we did model runs to look at different concentrations of coliphage on the x-axis at different taus, which are represented in different graphs here. So this first graph in the upper left-hand corner is for F plus coliphage, unaged sewage in the water. And you can see for different concentrations of coliphage that are measured in the water, we expect different distributions of illness. So the middle bar is the median. So for example, if you have fresh contamination and you measure 10 to the 1 PFU per 100 mil, that's 10 PFU per 100 mil, then you would expect median probability of illness to be about 10 to the minus 2. So each of these box and whiskers shows a different temperature, so 15 and 25, and you can see that the blue and the gray boxes start to look different for tau equals 5 days. In fact, according to the model, given the concentration of coliphage in sewage, you would never expect to measure a concentration of, say, 10 PFU per 100 mil after 5 days if sewage were the source of contamination, because it would have pretty much all decayed at that point and not be detectable. So it's hard to see here what the risk-based threshold is, what it is for this particular tau, it's the concentration for which the median illness crosses this horizontal line of 32 out of 1,000. So for tau equals 0, it looks like it's maybe somewhere between 10 and maybe 100 PFU per 100 mil, but we're going to look at that on the next slide. And the concentration where it crosses this line changes as a function of tau. So this slide summarizes that. So on the y-axis is the concentration of coliphage, and on the x-axis is tau. And this line shows the risk-based threshold, that is the concentration at which the median predicted illness is 32 out of 1,000 for different tau scenarios. So for example, at tau equals 0, fresh contamination for somatic coliphage at 15 degrees, the risk-based threshold is about 60 PFU per 100 mil. And as the sewage ages, the risk-based threshold goes down because the pathogens are decaying, and so is the coliphage. You can see that the decay with age is greater for higher temperatures because the indicator is decaying more quickly at high temperatures. And this grayed out area are concentrations of coliphage that are difficult to measure in the environment. So if you have contamination at your beach and you know how old it is, you can use this chart to figure out what your risk-based threshold is. So for example, if you're swimming in the chilly waters of Northern California and it's 15 degrees C in the water, and you know that your contamination is 4 days old, your risk-based threshold for somatic coliphage is about 10 PFU per 100 mil. And for F plus coliphage, it would be a little bit less than 10 PFU per 100 mil. So that's great, but normally we don't know the age of contamination in our water. So what happens if we don't know anything about the age of contamination? We repeated the analysis to determine the risk-based threshold when the age is unknown. And to do this, we specified a measured concentration of coliphage. And instead of pre-specifying what tau is, we said, okay, the age of this contamination could be anything between 0 and some maximum age. And that maximum age is the time at which one would observe that particular concentration of coliphage if the water was 100% raw sewage with a certain concentration. And here we consider two possible concentrations, which I denote Cmax1 and Cmax2. So if we apply that approach and model what the probability of illness will be, the results are shown here. So we have probability of illness log 10 transformed versus the log 10 transformed concentration of somatic coliphage and F plus coliphage for different scenarios. So different temperatures and different assumptions about the maximum concentration of coliphage in sewage. And where these lines cross 32 out of 1,000 is the risk-based threshold for those different scenarios, which I'm going to summarize on the next slide. So here is a summary of some select risk-based thresholds. So when the contamination is unaged, the risk-based threshold for somatic and F plus coliphage is 60 and 35 PFU per 100 mil respectively. And then we have different values here when the contamination begins to age 1 day, 3 days at different temperatures. For unknown contamination age, the risk-based threshold is between about 1 and 10 for somatic coliphage and about 1 for F plus coliphage, and it's not dependent on temperature. I know I covered a lot of information in this short presentation. I have a few additional notes here. So first, norovirus drives most of the risk in these models. And there's very limited decay on norovirus in surface waters, so that's really sparse. So we need more data on that. Lastly, I just want to emphasize that this work builds off the research of many people, and you can see the manuscript for a list of references. And lastly, just remember that the risk-based threshold based on all this modeling work under a number of scenarios is probably our best guess between 1 and 10 PFU per 100 mil. Thank you.